Hello, everyone. Welcome to TAF. I'm Jie, assistant professor in the Web Information Systems group at the TU Delft. Nice to see you and welcome. First, a very brief recap about the topic before introducing our speaker. So we look at human-centered AI, a broad topic that studies the design, development, but also the use and the governance of AI systems for better supporting human activities in a trustworthy manner. This series of human-centered AI focuses on the knowledge and language aspects, which are key concerns in making AI systems and humans understand each other and acting upon such an understanding through interaction. Now, on these topics, we have invited a list of speakers whose work has made foundational contribution to these fields. Now, this week, I'm thrilled to introduce our new speaker, Besmira Nushi, a principal researcher in the Adaptive Systems and Interaction Group at Microsoft Research. Her interests lie at the intersection of human and machine intelligence, focusing on reliable machine learning and human AI collaboration. She has made practical and scientific contributions on implementing and deploying responsible AI tools for debugging and troubleshooting machine learning systems. Currently, Besmira is leading the research behind several responsible AI tools for debugging machine learning systems, such as Responsible AI Toolbox, Error Analysis, and Backward Compatibility Machine Learning. Today, Besmira will introduce their work on on these aforementioned tooling, and all participants feel free to ask questions, but in the chat during the presentation. Before the end of the presentation, you will get the chance to open your mic and ask questions before the demo that Besmira is going to show to us. But after the demo, of course, please ask questions as well. Now, without further ado, let me welcome again Dr. Besmira Nushi. Thanks, Besmira, for being here. The floor is yours.
Thanks, G. Thanks again for the invite. It's a pleasure to be here in a human-centered AI audience. From what I see, many of the topics that you are talking about in this audience are related to trustworthy and responsible AI. So really stoked to be here. So today I'm going to cover some of the new releases that we had for Responsible AI Toolbox. And those are Responsible AI Mitigations and Tracker. This were just released basically 2 weeks ago, so everything is fresh and on top of mind. Before I dive into the content of the presentation, I also want to thank everybody who participated in this project. This is a collaboration between Microsoft Research, the Ether Committee, which is the committee at Microsoft that looks at AI and ethics and engineering, and also Agriculture for Machine Learning is basically one of the main groups at Microsoft that works on infrastructure for AI, both for first-party and third-party customers. So let's see what is the agenda for today. We are going to quickly cover the 2 new releases together with some context on Responsible AI Toolbox and previous tools that have been in the toolbox. We're going to go through a demo together with an end-to-end case study to see some of the main functionalities of the tools. And let's take a quick set of questions before the demo, just so we are all on the same ground and we all understand the concepts. And then we can take more questions after the demo. So our Responsible AI Toolbox is an open source framework for accelerating and operationalizing responsible AI with a set of interoperable tools, libraries, and customizable dashboards. This is an effort that we really started at the end of 2019 and 2020. The first release in this end was Responsible AI Dashboard. This is a dashboard for identifying and diagnosing responsible AI issues with mature techniques such as tools that were already part of the deployment back then, such as error analysis, fairness assessments, interpretability dashboards, data exploration, and counterfactual analysis. So something to understand about the dashboard is that it is available both as an open source tool and also in Azure Machine Learning for higher scalability and dealing with larger data sets. But one of the unique parts about the dashboard is the fact that it brings together these pieces that are all necessary for model debugging. Until the moment when we released the tool, we noticed that there is a lot of fragmentation, even in the responsible machine learning area, where we see one tool about, for example, fairness, one tool about interpretability, maybe another one about how to look at errors of the model. But when you're a data scientist, you want to do this thing in practice, right, for real models and data. There is many questions that come in and are all related to your responsible AI assessment and debugging, but they may touch upon different aspects of the model and the data. And that's why we decided to bring all of this together into a single workflow that is also customizable. And we're going to see later how this really works in a case study. The two new releases are Responsible AI Mitigations. This is a Python library for implementing and exploring mitigations on tabular data. So while Responsible AI dashboard is going to have some news on vision and language, basically in the next few months, Responsible AI Mitigations and Tracker for the moment deal only with tabular data. And that is mostly because of the nature of these mitigations requiring retraining and requiring redesigning perhaps models and data upon mitigations. Responsible AI Tracker, on the other end, is a JupyterLab extension for tracking, managing, and comparing different types of responsible AI mitigations and experiments, again, on tabular data. And you can find all these tools in their respective open source repositories on GitHub. So there are going to be two themes in this talk that we also believe to be differentiators for the project. The first one is targeted model debugging and improvement. And I'm going to talk about this in depth, but basically what this means is to understand the errors, where they appear, why they appear, and before taking an informed mitigation action. And the targeted model debugging is basically something that we are trying to bring as part of the clean data science practices and practices that can push the model improvements beyond adding data and adding more compute to the problem. The second theme that you are going to see here is the interplay between code, data, models, and visualizations. While there are many other data science tools out there, many of these make use of perhaps like one or two of these aspects. But if we want to really leverage all the power behind all these different artifacts in machine learning, we believe that one needs all these four different pillars to really make progress. And there's many examples of this, but we are going really to see this in the demo into how all these different artifacts can interact together and can be put together into a single tool. So what is targeted debugging for machine learning? We identified 4 different stages in this machine learning improvement lifecycle. The first stage is error identification, or broadly speaking, identifying responsible AI issues. One of the things that perhaps maybe the main contribution of this stage is disaggregated model evaluation. And what we mean by this is going between single score accuracy numbers that describe the model to scores and evaluations that are able to identify where the model fails. For example, many times in Kaggle competitions, in media articles, or even in research papers that we write together, we see tables that say the model is 90% accurate, but that does not tell us where the model exactly fails. So basically the slices of the data where the model makes more mistakes. So this is what happens in the identification stage. We try to identify these cohorts of data where the model makes more mistakes. And in the toolbox by itself, the main contributor here is Responsible AI Dashboard that works through the identification stage. So one of the concepts that is going to appear over and again in this talk is the concept of cohorts. And many of you may be familiar with this. Many of you may be referring to it in other ways, for example, as data slices or clusters of data. But at the end of the day, it's basically the same concept. It is a set of filters that is being applied to the model and to the data to discover these cohorts that have higher errors. For example, it could be people who live in Amsterdam, or people who live in Eastern Europe and work in technology. So all these are cohorts that are retrieved by having different filters on the data. And the next stage in this cycle is error diagnosis. And here we go back to either the data or the model to understand what was going wrong with the data or the model that led to the wrong decisions that happened initially on the first place on a particular cohort. And the responsible AI dashboard and mitigations are the main players here. And both these stages serve as an information stage to the mitigation techniques. Here, the responsible AI mitigations is one of the main players, and it offers a set of mitigation steps that are informed by previous stages. And then finally, as we know in data science, the story is not always happy and rosy. It's not that you try out one mitigation and it works out of the box. Generally, data scientists have to go through a series of them, but then you also have to compare them and understand where the things improve and where the performance decline. So something that we often miss out in machine learning evaluation, especially when it is an update to the model, like the model has already been deployed in the past and now we're updating it. Something that we're missing out is the fact that even though the accuracy of the model may increase, there may be new errors that are newly introduced into the model. And often we refer to these as backward incompatibility issues, in that new errors are being introduced to the model that were not there before. And these new errors are important for two main reasons. It may be because of a human AI collaboration reason. So imagine you have a doctor that is interacting with this model, and they have learned where the model makes mistakes and where it doesn't. And by introducing new errors, say if we look at this Venn diagram and we see the intersections of errors, we'll have a bunch of errors here on the red side that are new. They may confuse the user, and the user may trust the model in the parts where it is supposed to override or inspect them better. So this is the human AI collaboration side of the things in backward compatibility. But there may be other reasons, like if you have built a whole software that relies on this model, and you have learned how to fix some errors with the other parts of the software. If you introduce new errors, you will not be able to mitigate them in other parts. So as always, something that responsible AI teaches us is that many of these issues stay at the intersection of human-centered properties and how the system operates as a whole in a real-world scenario. So this sort of strategy or mindset is very different from many of the techniques, or at least it is complementary to many of the techniques that we see so far in model improvement, that are blanket approaches which either add more data or more compute to the problem by increasing the architecture size. These techniques are good for bootstrapping a good model, for building a model at the beginning. But then when you have issues that are related to particular cohorts or very specific responsible AI issues, then you have to take this sort of precision medicine kind of approach that can address some of the errors. So again, before we delve into the demo, I also would like to invite you to look and pay attention to the interaction between these different pieces of code, data, models, and visualization, and just let's imagine together what kind of tools, new tools, can be built if we are able to fully leverage the interaction between these. And of course, in the demo, you'll see some aspects of this, but there are even more powerful ways of putting all these pieces together. I'll say a little bit about that at the end of the talk, but yeah, this is what concludes, one of the first parts. Very quickly, responsible AI tracker that we are going to talk about later. This is a Jupyter Lab extension. I hope many of you are familiar with Jupyter Notebook. This is, of course, one of the things that is being used day-to-day in data science. But Jupyter Lab is the next generation of Jupyter Notebooks. And one of the things that it offers is the fact that you can work with more than one notebook at the same time for cleaner data science practices, so that not the whole code is within one notebook. And it can bring together many different things. It's possible to build visualizations with, let me just show you just a screenshot for this, but we're going to get the demo later. So basically you can look at code on the side, on Tracker. You can attach models to the code and say that this is the code that was used to generate this model, in case you'd like to go back later and track the changes. And it's also possible to build React components, visualization components within this framework. And this is just like one example of what we built. But basically, as long as it is a React component, everything is in the game, right? So as students and researchers, we can imagine many other different things that could be built within the same framework. So that was Tracker. Responsible AI Mitigations library is merely a Python library. You can pip install it through PyPy. This has a rich set of mitigations that focus on data quality. And so as you, many of you, during their career, they have looked at data from just like a pure data management perspective, or from an information retrieval perspective, or from a machine learning perspective. In many cases, we have looked at the data quality in terms of like, oh, does it have errors? Is it clustered enough, and so on and so forth. But here we are looking at the data quality as it relates to the quality of machine learning models, which is something that, it's probably, it's about time to do this in the machine learning community in some way. It follows a very simple interface that follows the fit and transform convention, similar to the scikit-learn convention. And we kept this standard just so data scientists can come in and just call these methods as they are. And it is also possible to customize these methods and calls by targeting particular features or cohorts. And this is where targeted model debugging comes in place, in that everything you do in this library, you can customize it to a particular cohort, and you do not have to deal as a data scientist with sort of like the dirty and tedious work that happens behind separating the data or slicing the data, doing something in different ways, different parts of the data, and then bringing it back together. Because this is one of the things that takes a lot of time in data science, wrangling the data. And it's possible to also apply different models to different cohorts, because in many cases, we see, especially in practice, that there are cohorts that have a very different dynamic than others, or different non-linearity from a machine learning perspective, and they will require some more attention. So in a nutshell, this is sort of like what is today available in responsible AI mitigations, the set of data mitigations that stand on this first column. The second column is the module that takes care of the targeted approach. Basically, we have a cohort manager class that can distribute different mitigation steps to different cohorts programmatically and with very few lines of code. There is a part here that is called decoupled classifiers This is research that came out of fairness research from the Cambridge lab and Cynthia Dwork at that time. And basically what they proposed was exactly to build different models for different cohorts and also apply post-processing thresholds for a fairness concern. In that, if the model has a probability score as an output, you can apply different thresholds and trade off precision and recall just by post-processing. So basically what we're doing is that we're mainly just enveloping this technique into our library to cover some of these issues. And then from a diagnostics perspective, we have a data balance analysis module that goes into the data and checks for different types of data balancing issues. And we'll see later why this is important. But we're building a lot more into the diagnostics process in the future in terms of detecting data quality errors. So just to give you like an idea about like what is the output of this library, imagine you have a data set, as we always do in data science and machine learning, and we would like to apply different mitigation pipelines here. For example, we can do scaling, imputation, rebalancing, and so on and so forth. With the usual, for example, you can apply or you can customize the pipeline itself. So basically the first 3 lines here, these are different pipelines. You can put Lego blocks, so to say, in these pipelines and build them together. But it is not possible to say that you want to apply one pipeline to one cohort and another completely different pipeline to another one. And this is basically what the addition that we are doing here with the library through the cohort manager class. Like imagine you have 2 different parts of the data, cohort 0 and cohort 1. Cohort 0 may be balanced and all you have to do is some scaling and imputation. But for cohort 1, maybe it is not as balanced. And you would like to apply one additional step to this one without having to explicitly separate it from the data yourself and do the other operation. So here you can build a custom pipeline that goes only to this cohort and does the rebalancing. And it's also, again, here at this part, it's also possible to output 2 different models. So this is just pictorially like how it will look like. I'm going to show later on how this looks in code. But before that, since we are like halfway through the presentation, maybe it's time to take some quick questions.
If you have a question, you can simply unmute yourself.
Yes, it's difficult for me to access the chat right now. So if there are any questions in the chat, I cannot see them, but maybe someone can just like read them out or.
There is not a question in the chat actually.
Okay.
Yeah, but well, I have a question, but it's not so much directly, you know, that urgent at this moment. I will leave it to the end. So if we don't have a question, maybe Besmira, you can simply go ahead and we will discuss afterwards. Oh, we have one from the audience. So the question is the following. For the mitigation library, how is it different than other libraries like IBM AIF 360?
Right. So in many, there are many libraries in this end, like the IBM library. There is FairLearn library also on the modeling side. So you can think about all these interventions or mitigations as happening in 3 different stages. One of them is data preprocessing. The second one would be during model training by adding optimization constraints or different loss functions. And the third one would be on post-processing. One of the main focuses of the IBM library is during model training. So basically with constraints or different loss functions. And this is the same for FairLearn. And the methods are different, but basically these are all based on this part that happened during model training. Here we took an opportunity to look at parts of the machine learning lifecycle that are not necessarily happening during model training, because they are just as important as the others, in that generally, you know, good data transfers to good models, and the opposite is also true. If the data is not great, then the model quality is also going to suffer. So here we are connecting the story between data and models, and also with the decoupled classifiers, we're offering some mitigation steps that happen after the model is trained, so during the post-processing time. Yeah, so if you think about this in like 3 different parts, we are doing part 1 and part 3, and many of the other libraries, like the IBM example, are focusing on part 2. And again, to have like a complete picture on this, one could use any of these libraries together for the best results.
Thanks.
Very good question. Thanks.
And thank you, Bhavya, for the question. If you have follow up, please ask. Otherwise, I think yeah, we can go to the demo, Besmira.
Can you read the text here? I can zoom as much as possible. G, how does it sound?
I can. It's a bit small
Okay.
on my laptop, but I can still.
Okay.
Oh, this is better, I think. Yeah.
Better. Okay.
Yeah.
Great. Thank you. So here, what we are going to do is that we are going to go through different mitigation steps by using the Responsible AI Mitigations library. We are going to identify the issues with the Responsible AI dashboard, and then compare them with Tracker. So this is what is going to happen. The scenario is based on a data set that I'm sure many of you have used, like the census income data set. The census income data set contains a list of features such as age, capital gain, education, number of education years, and it tries to predict whether a person gains more or less than 50K per year. And this is a very, common task in machine learning, mostly for illustration purposes. The data set is a little bit old by now, but for illustration purposes, we are going to see how all these features interact together and what we can find. So first, what we are doing here is just the usual thing in machine learning. We are training a light GBM model with 5 estimators that are gradient boosted by the library. And we are applying some very simple mitigation techniques here that are an imputer and encoder. And we are training a pipeline based on this. Now, imagine this is a model that you have used for a long time, and you'd like to understand what are the issues, or basically do that disaggregated analysis that I was mentioning earlier. So in this last cell here, what we're doing is that we are importing the Responsible AI dashboard. We are giving it as an input the training data, the test data, and the target feature, basically the one that is targeted for prediction. And then we are adding a interpretability component to the dashboard and an error analysis component. It is also possible to add other components to this dashboard. We will not have time for this today, but basically the dashboard has other components on counterfactual analysis and also on causal decision making, if this is something that you are working on. For example, if you'd like to understand just from a data perspective, the causality between different variables. But for here, we're going to focus on just model debugging, and we're going to look at interpretability, error analysis, and data. So let me just go to the top of the dashboard, and I'll have to zoom out back here just so we can see the visualization. So the first component here is error analysis. And the main goal of error analysis is to be able, through a very simple set of rules, to describe to the user how the error cases are different from the success cases. So what you can see here is a decision tree that is very simple, is trained on the error label. So basically, if you imagine you have a data set, and on top of the usual label that you want to predict, you also add a label, and this is happening all automatically in the tool, by the way, but I'm just explaining it for clarity. You add another label that talks about whether the model is right or wrong in that particular record, and then you train a very simple decision tree, and then the decision tree is going to tell you where these errors are concentrated. So let's see what this tells us. In this case, we're going to use two visual notations here. We're going to use the depth of the red color to look at the error rate, so how much error the model makes for that cluster and cohort. And we're going to look at this fill line here, which we call the error coverage. And basically that says how many errors that are in the overall data fall into that cluster. For example, here you can see that there are around 1,057 errors. The fill line, or the error coverage, is going to tell us how many of these fall into the cluster. So we can see that for this cluster, which is the relationship is different from husband and wife, which means that these are individuals that are not married, the error rate is only 6%. The overall error rate for the model is 20%. And for this cohort, which is people who are married, so the relationship is either husband or wife, the error rate increases up to 39%. So as we see, if we go just from the whole data to a slice of the data that is generated by having only one filter on it, the error rate increases twice as much. So the error rate here increases from 20 to 40%. And it increases even further if we look at people who are married, who have a high number of education years, in this case higher than 11, and who have a capital gain that is lower than 7,000. The error rate increases up to 65%. So in this way, we are able to identify parts of the data that have more errors. And again, we can also have other visualizations here. For example, this is the heat map, which is more manual than the tree, but it is very useful to look at very, sort of more fluid dynamics. For example, here I'm trying to plot the dependency between the error rate and the number of education years. And as you can see, as the number of education years increases, so does the error rate. So as basically what we can gather from this is that the model makes more mistakes when the number of education years increases. Okay, so let's see then what else can we derive from this tool. So we found out that the married cohort has a lot of errors. We can also look at this other component, that is the model overview component, and this is going to tell us about the usual metrics in machine learning, like false positive rate, accuracy, precision, recall, and so on. And from this, we can see that the model generally has a very good precision, but a low recall, which means that in some ways, it is missing out on individuals who earn more than 50K. So it's not able to make those kinds of predictions very well. And this is one more piece of information that is available here. But then let's go and see what happens to the data. So here, the data analysis component, and this, as you can see, everything here is modular in that all these components, you can just use them perfectly well by themselves. But now we are trying to use them in combination with the other components, just so that we have a flow. And we can see that there is some imbalance on the overall data, meaning that here there is more data for folks who earn less than 50K. And let's see how this data distribution looks like for the not married cohort. The distribution is similar to the not married cohort, but there is a little bit, just a tiny little bit more skew. And basically what we can derive from this is that the prediction problem is sort of easier here, in that the model could easily just say 0 and get things right. But for the married cohort, here there is a lot more balance in the data. meaning that the prior on this cohort is very, very different than the prior for the overall data. And that is why perhaps the model is making more mistakes. So this is the main piece of information that we are going to use later for the mitigation steps. And then we have another component that is on explainability. And here this is telling us that the main features that are being used by the model are marital status, occupation, capital gain, and number of education years. And you could use this component to sort of identify the relationships if they are healthy in terms of interpretability. For example, one thing that is interesting here is that this is saying that capital gain is important for income, while in reality, we know that it's the other way around. Income is important for capital gain. So if you were deploying this model in the real world, perhaps you would make some changes here and say that either you don't want to use capital gain or get more data in order to get the result right. So this is a current model, right? Like there is no major mitigation step that is being applied here. Let's look at this other model, and again, we are all doing this in the Jupyter Lab extension. So this is what we are going to try out here is a very simple mitigation step that is going to balance the data, because based on our findings, this was one of the main factors that was related to the model errors. So what we are going to do here is a very simple, I'm going to zoom back. It's a very simple mitigation technique. Here we are going to rebalance the data such that in the end, we see the same number of positive and negative labels. So if we visualize the data, how it looks like before and after the mitigation, we can see that after the mitigation, now we have everything perfectly balanced, but we have added more data for the merit cohort. In that, while we were expecting a little bit of a more balanced distribution here, because of the way how this mitigation techniques rebalancing works, is that when it is going to sample or generate more samples from the positive class, naturally, because more of the samples are located into the merit cohort, it is always going to sample more and more from the merit cohort. So much so that it is going to even change the prior in this particular cohort, and generally less in the not merit one. But let's see how this does. Like, we're going to compare the models now, the baseline model and the new one that was just mitigated. As you can see, through the mitigation step, we were able to increase accuracy by 4.3% in this case. But we also see that the precision has suffered in this case, in that the precision is not perfect as it was before, because we have gained a little bit more in terms of recall. So this is what we see in a glance. But then we also want to understand how things went for the merit and the not merit cohort. And you can add new cohorts, by the way, here with filters, like adding filters to the data with different options. But I'm going to save you from the details here, because I've created this before the presentation. So here we have the merit and not merit cohort, which I'm adding to the visualization. And here what we see in these comparisons is the numbers about how the merit cohort has improved. And we do not only focus on the aggregate numbers here, but we want to make a one-to-one comparison, so that if anybody comes in, for example, and just wants to compare the merit cohort, they'll be perfectly able to do so. And the numbers in brackets here are just the difference on the one-to-one comparison. So we can see that for the merit cohorts, we improved the things quite a bit. And the same for, like, the not merit cohort was already in a good accuracy. So the improvement here is only 1%. And we're able to look at all these numbers. And then the question is, like, can we do better than this, than the blanket mitigation, so to say, that is not targeted? So what we are going to try is two things. One of them is to balance the two cohorts separately, meaning we would like to have the perfect balance on each of them. And we would also like to sample the data in an isolated fashion from each of the cohorts. So if I say that I want to balance the merit cohort, the positive class here should only have merit people, and the not merit cohort, the same reasoning, right? So let's see how we can do this with the responsible AI mitigations library. So this is very simple with the library. What we're doing here, and again, I'm going to zoom in a little bit more, is that we are creating the cohorts. This is how you define a cohort in the library. It's just a set of filters. And we are creating two pipelines. These pipelines both do rebalancing, but they are going to do this in an isolated fashion. And the way how we make sure that these are isolated and targeted is through the cohort manager. We're saying that this is a set of pipelines and this is a set of cohorts. And this pipeline is going to be applied to this cohort and so on and so forth. And this is it. So basically, this is the whole code that you need to write as a developer to be able to do this in a customized and a targeted manner, right? So this is one thing that we are going to try. The rest of the code is basically just the previous code that we had on the initial model. And then the other thing that we are going to try out is to apply the rebalancing only on the merit cohort, because that is the cohort that had more mistakes. And so this part of the code is the same. The only thing that changes here is that we are going to leave the pipeline for the second cohort, the not merit cohort, empty. So we are not doing anything with this cohort. And then the rest of the code is the same on the cohort manager. Okay, so let's see, let's go and compare how this looks like. First, let's look at the one that balances both cohorts individually. And we can see here, so now we can see here that this mitigation technique that is isolating the two cohorts, it is not giving much. So it's improving a little bit with respect to the baseline, but it is not really, you know, giving us much. And in order to understand why, we go and look at the merit and not merit cohort, and we see that while we have improved things quite a bit for the merit cohort, even more than the previous mitigation that we saw earlier, for the not merit cohort, we see an 8% decline in performance. And again, this is like one of those backward incompatibility issues that happens here because of the data shift that we introduced through the data balancing for this cohort. So in this case, again, we think like, well, maybe we should not be touching the not merit cohort because this was okay from the beginning. And let's see how that performs, since we already tried that through the library. And we can see that indeed, if you do not do anything in particular for the not merit cohort, but only if you apply this mitigation to the merit one, you can sort of get the best of both worlds and have an even higher performance for this one by an improvement with 6%. So again, this is just an example about like how one can basically apply all these different mitigation steps. You can also bring in other mitigation steps from libraries like FairLearn or the IBM library and train all these models with different notebooks and register the models. I didn't show you how to register the model, but the process is very simple. So basically, if here you would give all the information about the data set and model and some extra information and just register it there to do the one-to-one mapping, and then after that you'll be able to show it in the model comparison. So this is for the demo. I think with this, I'll basically conclude by saying a little bit more about what we want to do next. Next, we want to gather all this information about what mitigation steps are applied to each models and to what data. And we want to apply AutoML techniques and meta-learning techniques that can learn from the different mitigations, from the code that is there in the data, in the notebooks, from the data, the models, and what we found out with our responsible AI dashboard to take all this diagnostics information and learn from it and be able to output a few mitigation suggestions to the user in the form of pipelines that they can apply and push more responsible AI mitigations in an informed manner without having to search for all of them, because sometimes some of this process can be costly in terms of time. So that concludes the talk. Thanks so much for attending and open to questions. Thanks.
Thank you, Besmira, for introducing the nice and important tool that you are building, and thanks for walking us through how it works using real code. We have a question already from the chat. Gala, do you want to ask yourself?
Yeah, thanks. So my question is actually, so what's your say? How can this toolkit to solve current, say, deep learning models? Because I know there are some, most famously maybe the pre-trained language models. I want to know whether say you can, your toolkit can be directly applied to say flexible, textual inputs.
Yeah, so one of the things that we are looking forward to release in a couple of months, so basically in mid-May, is the adaptation of this tool for vision and language. And one of the main differentiators about like how you can use them with vision and language is through metadata. So basically a lot of teams at Microsoft, when they work on vision models, they also generate a lot of metadata that is associated to the vision part of the data. For example, you could talk about things like objects that are present in the image, or you could talk about like how dark the image is, exposure, light, things like that, size of the bounding boxes. And you could try to understand how each of these factors impacts the error of the algorithm. And those releases will also focus on interpretability methods for vision, for instance, that we know are very important in that sense, like, for example, integrate gradients and gradcam. On the text side, we have also built a set of feature extractors. These are also open source, by the way, the feature extractors themselves. And these feature extractors can talk about, for example, whether there is a lot of gendered pronouns in the text to understand gender bias, for example, or if there is some sort of complexity to the text. Say, if the question is too complex, it has a very complicated parse tree, we try to correlate that with the error of the algorithm, in that perhaps the model didn't understand the question well because the parse tree was very complicated. So we built all these different feature extractors, and more can be applicable, right? These are just like an initial set. And we attach those to the text data and try to understand the model through that lens, together with other more language-based explainability techniques that I'm sure many of you are familiar with, like where the model puts the attention on different words, and so on and so forth, or like more black box explainability techniques as well, because sometimes, you know, we were discussing this even before this presentation started, that often we do not have access with the larger models to the model itself. So the attention-based mechanisms will need the model access, but if that is not available, then one can also try to use some of the more black box techniques like SHAP and others that are a little bit more computationally expensive, but can give you some insights to what words the model is using.
Okay, thanks.
Thanks,
So stay tuned. Thanks.
Actually, well, I just posted 2 messages in the chat introducing some of our work that was done on generating metadata for vision tasks.
Yeah, very, very useful, Jig. So that is one of the ways, basically, like one could use your technique to generate the metadata and then pass it to the tools to look at them in a more visual way.
Yeah, indeed. So what we were doing was also to With those metadata, we can then organize the images as tables, right? So that's
yes.
That's something that we did. Well, cool to see all the connections.
Yes.
We have two people in the audience raised the hand. I don't remember who comes first, but let's maybe start with Jacopo, because the other one, Bavia, you were asking before, so we come to you later. Jacopo, you want to go ahead?
Yeah, thank you, G, and thank you, Besmira, for your presentation. It was very clear, very interesting. I have a couple of short questions. The first one is you presented in your demo this nice tree visualization to detect the error based on this additional variable you create from the prediction of the model. And I was wondering, is it something that is that you developed for this tool, or is it an established technique in the literature? Is there some reference for that I can read more about?
It is, so there is, we did this based on research work that we did in 2018. I can post the paper here in this chat. So at that point, this was mainly a technique for us to discover cohort slices in the data that had more errors. So the whole paper is based on that. But it was not a tool yet. So we had developed the techniques, we had run experiments, we saw that it worked in many data sets and models, but it was not a tool yet. So it took us some time to build the right visualizations for it so that they are, usability is a large part of the tool building, and find out what are the good trade-offs with respect to the complexity of the visualization and how much information you really want to expose to the users. But I'll post the work here. It's from HCOM 2018. There are other techniques out there as well. So we focused on trees mainly because people cannot really go into the complexity of 10 variables and look at many different things at a time. So the tree gives some nice usability properties, but there are other techniques out there in terms of slice discovery that, like rules, for example, could be another way if you're looking in this domain. For the moment, we've had good results with this visualization. You could imagine of many other ways of showing things.
Yeah, thank you. And I agree very much with the usability part, not only because it's there in the literature that it can be easily applied. And yeah, so thanks for operationalizing it and making it more usable. And my follow-up question on that was, I am a lecturer at the TU Delft and I'm teaching a course on responsible data analytics. So the whole presentation was very interesting. Unfortunately, I missed the very beginning. So I was wondering, is there a way to get the slide or to get the links to the tool so that I can try and most likely also include it in my last lectures of the course?
Of course, I can share the slides with G, and then he can forward them to you, or you can drop me a line. Both work.
Yeah, and we will also release the video, I think on Wednesday, so it will be online on the TAF website.
Of course. Yeah.
So Jacopo, if you find it, if you have difficulty finding it, just drop me an email or knock at my door.
All right, awesome. Thanks to both of you. That was all for me.
Thank you.
Thanks. Bhavya, you want to go ahead?
Hi, hi, Besmira. Very nice
Hi.
presentation. I have a quick comment. First of all, I think this idea of decoupled classification, where you have different thresholds for different groups. I'm not sure if in the context of the US you can do that, because I guess there was some Supreme Court ruling based on that, where you cannot have different people for different thresholds. So I guess there might be some legal ramifications if somebody used in the US. So maybe you can put some cautionary line saying that use at your own caution, at your own will or something, because not sure if it will work out that well in the States. And second point I want to make is in the future work section, right? You talked about how you can use all of this data and model and visualizations to come to some kind of AutoML recommendation kind of setup. I'm just curious because in the demo you were showing these different interventions where you had different impacts on different groups and different metrics, right? But as we know that it is very hard to optimize for all metrics simultaneously, or maybe impossible in some context, right? So is it even possible that you can have a solution where you have perfectly, improved numbers on all sorts of metrics for different groups all the time? Is it even possible?
Yeah, so very good questions, by the way, thanks for bringing this up. So on the decouple classifier part, one of the things here, and you're right, in many cases, the sensitive feature may not even be available to the developer. One, second, even if it is available for just like testing purposes, you may not be able to use it to during training itself or during the prediction itself. And in those cases, this is something that is regulated by law, and you should just like not be using it. But even the model from the beginning, like the initial model, should not be using that feature as as part of the prediction process. But there may be other instances, for example, one of the cases that we were seeing on the vision domain is that one of the main factors that drives model errors in vision is the size of the bounding box. In that, if the bounding box is really small, then the model has a high chance for making predictions. And it does make some errors when the bounding box is large, but that is a little bit, like those are different types of errors. And those are the cases where many teams have decided to just like have a model that works on the smaller objects and then have another model that works on the larger objects, and that can sort of like improve the both parts of the system. So this is one of the cases where the or at least the feature that is being used for the definition of the cohorts is not sensitive, and it's something that you could use the decouple classifier idea. There may be other cases where, for instance, you could use think about like the medicine or the healthcare part. Like you could use the decouple classifier idea to build different models for different types of diagnosis or for different types of confidence scores. So, we don't have to be limited in using these ideas just on sensitive attributes. There could be many other attributes that, of course, do not leave the sensitive attribute, because that is also an important part to talk about that can be relevant for. And then on the second question that you were asking on learning and improving, you're right that in many cases it is hard to improve for everybody, but there are techniques that can, if they are combined together in the right way, they could at least improve the situation and not make things worse for certain cohorts. So imagine, for instance, you are applying an AutoML technique, just like, without the responsible aspect of it, just like the standard AutoML packages. You could imagine using these packages with a backward compatibility objective in mind. We have some papers around it, but basically the idea is very simple. During the loss function definition, you could decide to say that I do not want to introduce new errors, meaning that whatever I had before in terms of accuracy for certain content, I don't want to make that worse. And there are those functions that can be formulated like this, and they are very simple to run. They don't bring any computational complexity. And if we use this together, then at least we can make sure that we improve things for some of the cohorts that we had in mind to improve, and not make things worse for the others. So this is one thing. The other thing is in machine learning, even though we deal with data every day, I feel like we have not fully unleashed the power of the data in this part. We are often just taking the data for granted as it is. Like, take data from the internet, train a model. Take this data from different, enterprise data or tabular data, train a model. The data is not always perfect. The data may have problems. We know very well that when you sort of like merge different data sources, errors may occur. Humans may make mistakes when they label data or when they enter data because maybe they're tired at that moment, or maybe the task is subjective. There is a whole line of work on this, especially on crowdsourcing. And there is a lot that one can do to remove the noise or disambiguate certain things. I feel like we really have a lot to do in fully using the power of the data and bringing more data quality practices in this picture. So this is me saying that the story is not hopeless. There's a lot we can do on the data model, data side, and also the backward compatibility issues, so that we don't end up with a story that we just like improve some things but make some other things worse.
Just a follow-up question. Can you share those papers which have those loss functions where you can actually improve things and not make it work for anybody? I don't know that paper.
Yeah, let me. And there are follow. I'm just going to share the papers from our group here, but like there are follow-ups on that as well. So from other groups.
And just one last comment. So in the plot that you showed about the error analysis, where you showed the like a tree diagram, right? As you go down the tree, the number of samples go down drastically, right?
Yes.
So
yes.
the numbers, the percentages, can you simply compare them like apples to apples when the number of samples are much less for one group and much more for the other?
Yeah. So that is a question that we get very often in terms of like, even from an identification perspective, if you see these errors and the number of samples is not really high, like what do I do? Do I take this seriously, or do I, just let this go? I'd say if that cohort is important, the issue still needs to be taken seriously in terms of collecting more data for that cohort. In like one of the issues, for example, that we saw at some point with one of the vision models was that it was making more mistakes, and this was a celebrity data set, and you can understand the connection there. It was making more mistakes to do face recognition for women that were over 60. And that was because the celebrity data set had very few actresses that were over 60, or that at least looked over 60 in the images. But that cohort was very small. It was just like 20 people in that cohort. Now, what do I say about it? Like, I know very well that there is very little data in the celebrity domain because of the nature of work and many other societal biases. But if the model is failing half of the time, then this means that maybe I cannot really estimate the error rate for this cohort. That is correct. But that also means that maybe I should have more data for this cohort so that I can really estimate the error. So I'll say, take the error rate, the number, with a grain of salt, but take the problem seriously anyway.
Yeah, exactly. So if there was some way, like for example, we talk about intersectionality, let's say, right? And we talk about intersectional fairness, for example. So let's say we talk about a group of people who are females, who are Muslim, who are Black at the same time, let's say, right? So the number of samples goes down drastically as we add more number of attributes, right? And in such a case, like if we say that, oh, there were only 5 samples for a particular subpopulation, and the model performed bad, so hence the model is biased against those people, right? Yeah, it is like, you can say it in one way, but it can be, I don't know how much accurate that statement might be, considering that the model has seen very few samples of this particular subpopulation, and hence, yeah. But you're right, like gathering more samples one way for sure. But I was just referring that maybe in the visualization you could have some kind of visual, feature that tells you that okay, this is very a big percentage, but from a very small population, right? So take that for what it is and not just see the number for the number basically. So yeah, that might be something.
Yeah, there's many hints that we can give there. And again, like one still needs to take the small cohorts seriously, not for the numbers that they show in terms of the error rate, but just for the fact that they are small. And if they're also small in the training data, then we have a much larger issue there.
I'm sorry to interrupt.
Thank you. Yeah.
We're 8 minutes after 5. I'm not keeping my word, Besmira. But we have one more question in the chat. So if you can still stick with us for 1 or 2 minutes, that would be great. Otherwise, we can leave it online.
Sure. Like I have 5 more minutes, Jay. Yeah.
Okay.
Yeah.
Then let's maybe go through this last question from Arun. Arun, would you like to ask yourself?
Yeah, sure. So that's just like so I saw some of these old collaborations with Gagan Bansal. So I was just interested to know if you're still working with him on these.
Oh, Gagan is in my group now in Microsoft Research. He finished his PhD and he's in our group. Yeah. So yes, we're still working together. Yeah.
Yeah, because there are some ideas that we are exploring in our end, which might be it might be great if we can chat about it. Then that's what.
Drop us a line to both me and Gagan, and yeah, we can see where we go from there.
Sure. Thanks.
Thanks. Maybe one last quick question from me, if you don't mind, Besmira.
Yeah.
So in the error analysis, you have those features that can be selected, indicated cohorts, right? Would it be possible for the user to specify themselves? Let's say, for example, different combinations of features. Because that can link for that they can use the domain knowledge, right? What are important
So what is possible, if I understand your question correctly, is that it's possible to give more features to the dashboard. It is possible to create cohorts with different types of combinations that are not only I'm just trying to get back to the wall. So it's possible to say that you want to create a cohort with particular combinations, like you want age to be of this and that, and you want profession to be of some other values. So it's possible to create those custom cohorts as well.
I see. That's cool. That's cool. Because I was imagining in real use case, right? That maybe with some domain experts, they might have things in their mind that they would like to check. So that would be. Thank you. If there are no more questions, I think we can finish here. So thanks once again, Besmira. It's a great pleasure to have you here.
Thank you.
And thanks everyone.
Thanks again.
Thanks everyone for joining. Next week, we will have Fabio Casati from ServiceNow to introduce their work on trustworthy AI in enterprise. So see you next week.